Hello everyone, my name is Chih-Chen, and we are from AMD. Yeah, thank you very much. And today I'm going to present neural intersection functions, which is invented by me, Takahiro, and Shin, right? And what is NIF? NIF is a novel approach to accelerate finding ray intersections, especially in Monte Carlo ray tracing, utilizing neural networks. So for today, I'm going to talk about the problems that we have in Monte Carlo ray tracing, and that motivates us to develop NIF, as well as the design philosophies of using NIF. And we're also going to talk about how to integrate NIF into the conventional ray tracing pipeline so that everybody can use it. The rest of the parts, the experimental results, and the limitation, as well as the conclusion, will be covered by Shin later. So let's jump in very quick. So Monte Carlo ray tracing is very active research, and it has many potentials that's been known. And usually, in order to find ray intersections, usually a two-level BVH is employed. What is the two-level BVH? Conceptually, it's like this. We put objects in the scene into boxes, and we arrange them hierarchically. And then we also, for each object, it is also composed of maybe geometry primitives, such as triangles, and we also put those triangles into maybe smaller boxes and arrange them in a hierarchical way. Whenever we want to find ray intersections, we will first traverse the top level until we hit a bounding box at a node, at a leaf, and then we continue to traverse the bottom level of the BVH. And this kind of process is not good to run on GPUs. It's not effective because it is an irregular algorithm, which means during the process, we will have many branch divergence, memory access irregularities. That's not good for SIMT architectures. So overall, this one is very expensive. So that motivates us to develop NIF, this kind of approach, which is we want to replace the most irregular parts of traversing a BVH with something that comes from neural networks. And the benefit of doing this is by using neural networks, that translates the algorithm from a very irregular one into a regular program. Because inside a neural network, especially for the one that we are using, which is the multi-layer perceptron, MLP, the components or operations that is inside is mainly dense matrix multiplications, which has like regular patterns, regular memory access patterns, so that we can pre-customize or pre-optimize what kind of operations that we want to perform. So as being shown in the figure, we want to replace the bottom level BVH, which is usually the most complex part, with neural network operations. So the first thing we need to do is to formulate the problem set. So we identify the core operations of Monte Carlo ray tracing, which is the visibility test. So given an array like this, for example, if an array is expressed as a position P along with a direction D, and we want to identify the function, which is the visibility test itself, to report us 0 and 1, which means if the ray is occluded or not. And then we want to design a neural network to approximate this function at the same time. We want to sorry about this one. At the same time, we want to consider how to better utilize the resource that we have. For example, the number of rays being sampled, as well as the training time, the training efficiency, and the runtime efficiency. So the challenge here is we need to tackle how the resources are used effectively, as well as how to approximate this function accurately. So our main contribution can be listed as follows, which is to improve the accuracies. Three categories, three kinds of aspects are used. The first, we need to identify the alias rays in order to let the training process much more effective. And then we need to partition the problem set itself so that we can use as minimum resources as possible. The third one is, in order to train the network effectively and cover a wide range of data sets, we want to leverage a kind of encoding method, which is called grid encoding, to discover features that can be expressed effectively. So the first thing is to identify the alias rays. So the concept of alias rays is as follows. So in here, we can see there are two rays, which is represented as P1 with a direction D1, and P2 as its origin and with a direction D2. If they will hit the same position on the objects, we want to represent them identically for the network that we want to train. how do we do that? We found that we can utilize the bounding box itself. For the bounding box that encapsulates the objects, if we move the hit point from the actual hit point to the bounding box and use that as a representation, then P1, the ray represented by P1 and P2 can be expressed identically. Yeah. So based on the observation of this bounding box, then we design the network. So based on the position of the rays, there are two possibilities. If the rays are outside of the bounding box or they're inside. So based on this one, we designed two networks to handle different cases. The first one will be the outer network that we called. For those rays that are outside of the bounding box, that is being handled, that will be handled by the outer network. So starting from the hit point of the shadow rays, with the ABB. Now the hit point is respect to the bounding box itself. So as you can see, P is no longer on the surface of the ground, but on the bounding box. And then we convert the original representation of rays and directions from 3D the dimensions to 2D. And I will explain the benefit of doing that. The first benefit is that we can reduce one dimension. That is obvious. The second benefit of reducing one dimension is that right now, by converting them from a 3D space to a spherical coordinate, we can use them as indexes to something else, which is our grid encoding. So the reason why we are using grid encoding here is because we found that it is very difficult if we only supply the 2D input as an input for the network for training. Because sometimes the high frequency details of the scene cannot be expressed effectively, so we will lose some information. So we're thinking, how can we capture this kind of phenomenon or representation and to represent them or to express the data much more compact and expressively? So here, the grid encoding is used, and we utilize the original values, which is converted into spherical coordinate as theta and phi as indexes to the grid. Inside the grid, there are trainable feature vectors that will be retrieved when being indexed. So here, so sometimes the value itself is not integer, so it will not sit directly on the cell itself. So here, the bilinear interpolation method is being used to get the actual trainable features vectors. For the inner network, that will be very similar. But instead, now we need to consider if the object itself is concave. If the object itself is concave, there will be many possibilities of the hit point inside the bounding box. Then again, since we are considered the distance from the hit point to from the origin to the hit point, we want to represent that compactly and expressively. So we also utilize r, the distance, from the origin to the hit point as an index to a 1D grid as well. So in the 1D grid, it's a very similar concept as in the outer network. It stores a trainable feature vectors that can be retrieved later on. So this is the overview of the network. As you can see from the left-hand side, for each object, we will have a bounding box. And based on where the position of the ray is, it will have two type of situations. For example, in here, for the outer network, we're utilizing a direction grid and a position grid. And inside those grids stores training factors. Once we retrieve those training factors, we concatenate them to form the actual input to be trained in the neural network. And during the back propagation process, those trainable features stored inside the vectors will also be trained and updated correspondingly. The inner network is very similar, except that it incorporates another grid, another 1D grid, which is the distance grid here as well. And this is the results. No, this is the ground truth of this method. So in here, this thing, you can see there are like 3 objects, 1 bunny and 2 teapots. And this thing is being rendered by image-based lighting. And this is the result of NIF. As you can see here, I want to tell you that this thing is only being trained for 20 samples per iterations per frame, 20 frames, 20 iterations per frame, sorry. Yeah, but as you can see, for this small amount of training iterations, most of the details can be preserved. And you can also see where those results are coming from. For example, the blue one is coming from it's being inferred by the inner network, and the red one is from the outer network. Yeah, and this method will not be very useful if we cannot use it. So here I want to explain how this one can be easily integrated into the conventional ray tracing pipeline. So starting from the camera itself, so we can still cast the primary ray of the camera as usual. Then we cast the shadow rays whenever we hit something, right? And then we start to traverse the top level BVH until we hit the node on the leaf. And then one thing that needs to be taken care of is now we store the input data instead of traversing the bottom level. So we will have after this process we will have a series of trainable the data that we want to invert. For example, the directions and the position of the grid of the rays, and then we convert to the grid indexes as explained before, and then we execute NIF. So that will include to look up the indexes in the grid to retrieve the trainable factors, and then we use those trainable factors to infer the MLP. Yeah. So this is the actual architecture in details. So here, as I explained, for the outer network, there are two grids, one for directions and positions, and they are in 255 square as a resolution. And for each one, we will retrieve trainable feature vectors. Here is both of them are 3D, so by concatenation, there will be 6D. And then we supply this one to our MLPs. The MLP itself contains 2 hidden layers, which has 64 each nodes. And then at the end of that, there is a signal activation function, which reports and probabilities between 0 and 1. And for inner network, the architecture itself is very similar, except that there are more layers, but each one has reduced number of nodes, and the resolution of the grid is smaller. Yeah. And the rest of the part will be handled by Shin. Thank you.
Yeah, can you hear me? Okay, thanks. Yeah, from here, so as Chih-Chen said, so I'm Shin, so I'm presenting here. So using these networks in the previous slide, we evaluated the performance of NIF compared with the BBH-based implementation. So we implemented them using C++ and HIP for the GPU programming language, and we evaluated it by rendering images with Full HD on the AMD Radeon 7900 XTX GPU. And also we use some support on this GPU for the optimization of this implementation. So right there, for the BBH-based implementation, it uses state-of-the-art SAHBBH builder with the support of the hardware ray tracing cores. And also neural network execution on NIF uses the WMMA, so wave matrix multiply accumulation instruction. This graph shows the comparison of the secondary recasting time between NIF and the BBH-based implementation, and we evaluated them with 9 Shins. The top colored bar shows the NIF performance, and the bottom white bar shows the BBH-based performances. And the red bar contains top-level BBH traversal and the input data collection. And the blue and the yellow ones indicate the feature vector lookups from the grid encoding. And the green and the purple ones are neural network inference times for the outer network and the inner network, respectively. And also seeing this comparison, the performance improvement varies depending on the scene. But for the best cases, this one, so NIF reduces the secondary ray casting time about by 35% compared to the BBH-based implementation. So in this high stature scene. But what's the factor deciding this performance gain of NIF? So then, let's see it a bit further. These two figures show the NIF's ray casting time arranged by the number of polygons in the scene and the number of rays processed by NIF. So seeing the left figure, we can find that NIF has nothing to do with the number of polygons in the model. However, seeing the right figure, we can find it's almost linear to the number of rays processed by NIF. So therefore, because NIF's computational cost is not proportional to the model complexity like these images shows, then NIF is more effective when it's applied to the complex geometries. And if it's applying NIF to the model with a low complexity, it could not gain much benefit from it. Again, seeing this comparison, we can see this nature by focusing on these two Shins, Thai statue and Thai statue row Shins. So these Shins look like these. So although they look almost same, the number of polygons in this Thai statue model is different. On the left Thai statue Shin, so it contains 10 million polygons in this model, but in the right Thai statue row Shin, it contains just about 0.5 million polygons in this Thai statue model. So because of this model complexity difference, the BVH raycast time takes about 50% more than that on the left statue model due to the bottom level BVH traversal. And on the other hand, NIF only takes about almost same time, about 260 microseconds for both Shins. So as a result, we can see applying NIF to more complex model is much more effective, as we can see with this speed up result in the bottom row. So the left Shin shows a 1.5 speed up comparing to the the right BVH-based model. And from here, we will show rendered images for these two Shins, statues A and statues B, which show about 40% performance improvement. And you can find more rendered images for other Shins in our paper and the supplemental document. So please check them if you're interested in. So first, this is the Shin of statues A. So it's rendered with a BVH-based ray tracing. And this is NIF. Probably it's hard to see here, but yeah, this one is NIF. And this is rendered with ray tracing again. And this is NIF. Yeah, and yeah, another Shin statues B. So this is rendered with BVH ray tracing. And this is NIF. So, and again, so this is ray tracing. So this is NIF. So probably it's on this screen, so you can't find any difference on this. So please check the letters on our paper to further detail. But yeah, actually, so there is some difference, but the rendered image using NIF still preserves the image quality while improving the performance here. Additionally, we demonstrate NIF can also accelerate raycasting in a more complex Shin, and can be used in one unified rendering framework. We test NIF in this Shin where 6 complex models are placed in the bistro Shin. As explained before, applying NIF to simple objects is not beneficial. So in this test, we execute NIF only for the model with which have more than 100,000 triangles. And for other simpler models, so we just traverse the bottom level BVHs as usual. So even in this case, so NIF reduced the secondary raycasting time about 15% while preserving the image quality. So again, I will show there some comparing result, ray tracing and NIF. This one is ray tracing result, and this one is NIF. So again, so this one is ray tracing, and this one is NIF. So actually, again, so it's hard to see on this screen the difference, but yeah. We can say the difference is relatively small, and yeah, if seeing only these images to you, we believe you can't make a decision that this is rendered with our NIF approach. So you can't, yeah. I think so, yeah. Sorry. Anyway, so yeah. So this is a NIF rendered image, and to show the applicability of NIF to other types of rays, we also tested to apply NIF to primary ray casting. And yeah, in this scenario, the input to the network are same as before, but for the output, so this time instead of inferring the visibility, the network outputs shading normal and the depth from camera, which is a 4-dimensional vectors. In this application, errors of NIF directly result in visible artifact, and the accuracy is honestly still not enough compared to the BBH lane casting in this case. But yeah, let's see some result here. So this shows a result with a simple Bunny model. Left one is using the ray tracing, BBH-based ray tracing, and the middle one is a result with our method NIF. In this simple case, so it seems NIF shows a kind of good result. And on the other hand, seeing this result with Dragon model, we can see some degradation on the result with NIF here, especially in shading normal like this. So left is a ray tracing result, and right is a NIF result. So yeah, actually, so improving accuracy is one of our future work. So yeah, finally, let's discuss with the limitation of our approach here. So first, now in our approach is we focus on just the visibility of the secondary ray, although we have shown some application to the primary ray casting. So extension to other types of rays with improved accuracy, such as more deeper rays of shadow rays, is our interesting future work. Also, NIF is trained only with the rays based on the current viewport. So, so we need to train NIF again in order to achieve better accuracy for other viewports or other light sources. So again, so extension to dynamic scene, extension to animation also remains our future work here. And this is kind of not a limitation, but yeah, actually, so our current implementation of NIF can be further optimized by reducing the redundancy. So for example, like this image, so we're executing NIF for this pink ray, so this 2 times for the 2 hit point red and green. And but yeah, we don't need to, if the intersection point is found on the red hit point, then we don't need to execute anymore for this pink ray for the green hit point here, because its intersection point is already found. So like this, so we can further optimize it for our implementation. Then to conclude our research here, so we introduced a novel method using MLP to accelerate the ray casting time, so called the neural intersection function. It works as an alternative to the bottom level BBH traversal and can be integrated into the existing ray tracing pipeline, which has been never shown before. We also shown NIF can represent geometry with sufficient accuracy with improved performance. In order to achieve good result, we propose to use 2 different networks, outer and inner network, and the specialized input parameterization for grid encoding. And also our experiment demonstrated NIF reduced the secondary ray casting time by about up to 35% while preserving the image quality. So yeah, finally, that's our contribution, but finally, so the application of neural network-based methodology in computer graphics area is a kind of emerging technology. So, however, the efficient integration of the neural network into the conventional ray tracing pipeline is requires more further explanation. So we hope our research is a kind of starting point, and yeah, we inspired more future research in this direction. Yeah, that's all. Thanks for watching, and yeah, any question?
All right, so we have a couple of minutes for a couple of questions, I guess, or maybe just one.
Very nice talk. Do you have a table on memory consumption where you basically compare adding up the 2 neural networks versus the, let's say, compressed BBH or something like that? Or can you just tell me, is there a factor in between?
Sorry, I couldn't hear. Can you understand that? Can you hear the question?
Oh, sorry. So
yeah.
Should I repeat? Sorry about that.
Yep.
So it's all about memory consumption, right? Do
Ah.
you have a table where you compare the memory consumption of the 2 neural networks, right, versus, let's say, the compressed BBH that you use? Do you have such a table?
Yes, we do have such a table, and I think I can't remember the exact number, but I think if we utilize the grid itself, the grid is in constant memory.
Yeah.
So that we need, for example, for the outer network, we only need 2 type of grids, one for position and direction, and depends on the resolution that we configured, that will cost us constant memory.
And
yeah.
how big in bytes is the, let's say, the neural networks?
I think for the grid,
Yeah.
right? For the grid encoding, and we are utilizing 3 dimensions, and the one of the elements inside the trainable vector is like 32 bytes. So it's like 32
Yeah.
bytes times 3 times depends on the resolution is 255 square.
And also, we additionally, so we need more memory to further the weight of the neural network. But the neural network is shared for the all objects, so it's a constant for the. So it's kind of small.
Okay, got it. Thank you.
So single object is represented around like a 300 kilobyte. That's it. So even like a 100, like a 10 million like polygons, it's compressed into 300 kilobyte. So it's very like aggressive compression.
Yeah. Thanks for additional answer.
Very interesting talk. Is there a restriction on the execution of the neural network that needs to be in like wavefronts in order to utilize like the equivalent of tensor cores, or?
No, so our implementation is not to utilize that tensor core or something like that. So for the hardware implementation to accelerate the neural network. So, yeah.
All right.
But for training, we do utilize the wave MMA.
Yeah.
To speed up the matrix multiplications and accumulation.
So there's no acceleration at inference.
Mm-hmm.
Okay.
Yeah. We do, but
Yes.
it's just a software implementation. So so it's not to utilize any hardware core, hardware accelerator for the neural network.
Okay. Thank you.
Yeah.
I think this will be it. Another round of applause.
Okay.